So maybe I'll just sort of give you guys an outline of what I'm going to talk about, and then I'll actually start talking. So first, I want to just give you a little neurobiology. So what exactly what physically we're talking about is the offense. I'm not going to talk so much math, but it can get easy to get lost in the math and stop remember what you're actually trying to model. So I'll just tell you a little bit about that, and that will come in handy. Some of the other stuff. Then we'll talk about encoding and decoding. How that's done, or at least potential ways that's done. Then we'll talk about noise, where it comes from and how it's dealt with, and the sort of surprising idea that sometimes by having more noise you can actually enhance your signal-to-noise ratio pretty well. And then if there's time, and I'll try and make sure there's time since this is what you came for, we'll talk about neural networks, or a neural network. Okay, so out of curiosity, how many of you know what a neuron is? Okay, so then I'll just go through it real quick. So there's sort of three parts to a neuron. The three main parts. There's the dendrites. These are where the connections to other neurons are. And there's the cell, the nucleus. That's where sort of the processing goes on. And then there's the actual. This is the axon, and then you have the synapse, right? Synapses. So does anyone know how many neurons there are roughly in the brain? Okay. Why guess? Anybody else? It's like about 10 billion. Something of that order. Close to 100. And within like a square or cubic millimeter, you have about a kilometer worth of So we have this. Does anyone know how, or first what neuron firing means?
It's like when it's activated and it starts to send signals.
Yeah, okay. Do you know what that means, sending signals?
It sends signals to the brain.
I guess. So firing is equivalent to sort of an electrochemical pulse or an action potential, which means you get effectively like a voltage, or you get a sort of current going through your neuron. So you tend to make a little bit of electricity. So this is how does that happen? So if we look at the nucleus, there's a lot of potassium ions in here, and a lot of sodium ions outside. Yeah, and so. Yeah. So we have to. So what happens is for firing, their gates open up. So here, this becomes permeable to sodium, and so it comes into the cell, which raises the ionic potential inside the cell, and then that starts to force this potassium to leave. And what you get if you just draw sort of the voltage. Starts out, the neuron always starts out with a negative voltage, that's like negative resting voltage. And then it goes up, and it comes back down, and then sort of undershoots where it was. This is where it was. So this sort of rise in potential is what firing is. And then this period right here, which we're not going to talk anything about, but it's has a lot of loops. Right? So 2 neural models is a refractory period, so for a little while, this amount, the neuron can't fire, and has very low probability of being segregated, even if you put a lot of, you drive it really hard. Okay, oh, and then the last thing, sort of on the neurobiology side, is what's called a spike train. From these, so just to talk about what they are. One way of representing spikes through time, so the kind of graph, time is going this way, and then I'll make a mark like this if the neuron we're interested in fired at that. So this is just a way of graphically representing how the neuron fires through time. Oh, okay, and one thing I forgot to say, but it's actually very important, and you can sort of maybe guess from this, but which isn't, at least I didn't think it was intuitive when I first heard it, was that all the firings, all the action potentials are stereotypes, which means they're all almost exactly the same. So no information is passed on in the shape of these. If that makes sense. So all that matters is that there is some spike. It's not that this, like, you can't have a neuron that spikes much harder if you. So, sort of cover the neurobiology. Because now we're going to get more into the meat of it with encoding and decoding. So, what does encoding mean? Yes, at least in this context, there's lots of different ways that I guess. Kind of, yeah. Yeah, no, I mean, that's, but maybe more in this neural context. Oh, so I guess I didn't talk about it. So how does this, why does this happen? Why does this change in, or exchange of ions happen? That happens because at this synapse, two synapses. Yeah, exactly. So like, say we're looking right here, zooming up top. So this is some other neuron synapse, and this is this neuron's dendrites. So this is the dendrite, and this is the synapse of the other neuron. Then there are these neurotransmitters, little vesicles, and when this neuron fires and there's an action potential, it releases these things, and these things come out, and then they get grabbed by receptors. These are neurotransmitters. And these are, and then when enough of the receptors are occupied, or like they've received enough neurotransmitters, then this neuron right here, it'll okay, so coding, going back to coding, what encoding deals with is turning the signal, or the stimulus. So for instance, like you hearing my voice, those actual sound waves that stimulate the little hair in your ear, turning that stimulations into a language that the brain can understand. The language that the brain can understand, and that is just in terms of spikes. So effectively, encoding is how do you turn some real-world stimulus into spikes. Makes sense? Okay, so and so to sort of motivate this, or start talking about this, if I had to say, if you had to give an analogy of the brain to describe it as something else, what would you describe it as? Good. Any other analogies? if I was asked, I would say compute. But there's, and probably of all the things we have, the computer is most similar to the brain. But there's a sort of a problem with thinking about the brain as a computer because there are a few key differences. And this is something that's not new. Sort of all throughout our humans beginning to think about the brain, our analogies have always been tied to the technology at the time. So one of the simplest models, one of the first models of how the brain encodes information was by this guy named Redman. I think 1928. And so technology at the time, 1928, was a lot of, I mean, even though electricity was beginning to be a thing, it was still more that it was coming out of the steam age, but better steam engine age, but you still had it was very mechanical. So you have engines, pistons, and so his way of thinking about the brain as well, if I sort of apply pressure, well, the neurons fire because of pressure that's been pushed. So his model was that the rate of firing of a neuron, so the mean rate, which we define as the number of times fired over some time t. Just the mean, just as in the normal case we learned about, the mean rate of firing is proportional to the amount of weight you put on a muscle. So he had some tau or something, and he hung different weights from the tau's hoof, and he put an electrode into the brain, which is an electrode, I guess I should say. An electrode is putting with a little measuring device right here, and you measure the change in potential that's here. So that's how you can actually see when a neuron spikes. And so he put that into a power side somehow, I forget which one, while hanging different weights on his hoof. And he found that the more weight he added to the hoof, the more that neuron that he was looking at fired. And his explanation was, well, it's just like a piston or something. The more pressure I put on a region, the more the neurons fire. So everything that we described is just pressure. We know that's not true. But again, I think the reason I bring this up is just because for good reason we think of the brain as a computer, but like I'm just going to say in a minute more concretely, there are issues with thinking about it that way. It's not a computer, and when we're sort of tied to that analogy, our models are wrong. Which obviously there's not so much we can do because that's what we know, but it's good to think about those limitations. Does that all make sense? Never come up with a good way to write on these slidey books. Okay, so if it's not this sort of pressure method, I have to go back to why the brain's not a computer. Yeah, with computers, they run on binaries, so zeros and ones. And all the computations done in terms of zeros and ones. And like I told you here, where I said that the neuron, the firings are stereotyped, you would think, well, then either you're at a 0 or you're at a 1. Either you're firing or you're not. And so what's wrong with that now? Right? Why can't I think of this as a computer where it's running on sort of a binary system? And the answer is, well, say I take two spike trains that are like this, and I look at this point in time. Start. So at this point in time, both this neuron, so neuron 1 and neuron 2, neuron 1 is firing, so it's got a 1. And neuron 2 is firing, so it's got a 1. But, so with the binary sort of idea, you can say, well, these guys are doing the same thing. They're representing the same sort of computation and same sort of stimulus. But if you sort of zoom out and look at a bigger time window, you realize that this is very different from this because there's a lot more activity going on, right? And so looking at just the zeros and ones, whether it's fired or not, actually doesn't give you the full amount of information that you need. And some fancy theoretical work that was done in the 50s showed that you really can't think of the brain is just sort of a system of logic gates, so just zeros and ones. And what really matters is the rate at which you're firing and the time in between the neurons. Really, the time in between the spikes. So now I'll give you two more, slightly more complete encoding models, but that both have some issues. And then we'll talk about populations of neurons encoding. I guess I should have said I'm sure you guys know, like, if you're confused or have any questions, just stop me. So the first model it doesn't just use this binary representation, but actually takes into account other spikes, and sort of the timing is just the rate-based model. Rate-based. What does that mean? That means that say we have a neuron, say we have a decoder. Oh, sorry. So say we have some sort of stimulus. We have the eye. Wants to encode this tree, or at least part of this tree. Well, I guess the eye is trying to encode all of the tree, but we're just going to focus on one neuron, and that'll just be focused on the fact that there's something green right here for the part of the tree. Now, how can it do it? Well, this model says that it can encode the green simply by the number of the rate at which it spikes, the rate at which it fires, and so. The rate, we're talking about the mean rate as before, so let's try the rate here. The mean rate, just the number fire over some time. So if this is time here, then we have 3 fires. So the mean rate is 3 over 2. And so you can sort of imagine sliding this bit, this time window across and taking it. So we go back to maybe a slightly more interesting stimulus instead of just looking at the tree. If like you see a white dot, and then it goes black, and then you see white and white again, so you have a white circle, and then another circle, and then a white circle, and the way you encode a white circle is a bunch of spikes like this. Then your spike train would look something like this. Where this corresponds to this white circle, this corresponds to this white circle, this white circle, and this corresponds to and the nice thing about this is it's fairly easy to sort of compute if you have this whole spike train, and it's sort of intuitive. The issue is that there's no real good decoder in the brain. By that I mean, in order to actually average over a certain amount of time, you have to have memory, so you have to remember how many spikes have occurred in this time window, and you have to wait a while. And we know that, like, if I throw a piece of chalk at you, you move very quickly, or much faster than you would. I guess chalk is slow, but stuff we react very quickly, and so it doesn't seem like this would actually be possible because you have to have a time window like this to actually happen. Does that make sense? Now we'll talk about another single neuron model of encoding, which is rate-based encoding the time difference. So this model gets rid of this problem where you, instead of having to wait for like a very large time window to average over, you just need 2 neurons or two spikes, and you just compute the difference in time between. So if this was T1 and this was T2, then the way you encode information is by varying the difference of your the spikes. So information, so stored by t was t2 minus t1. The difference in time between this one fire and this one. So like if you're just seeing it as sort of a stationary stimuli, then you would expect the spike train to be very uniform and have the same distance here and here and here. Because you're saying you're getting the same, you have the same stimulus, and you're coding the same amount of information. But there's a problem with this, and this is more just an experimental problem, which is when you actually look at single neurons. Say we just look at the same neuron and we perform an experiment. This is the same neuron and we perform an experiment 3 times. We're imagining that we're getting rid of any sort of bias that might happen by like learning or a bunch of other things, because we're letting say we're looking at rats neurons, we let it like run free for a little bit, and then we look at this neuron and we let it run free, and then we let it look at the same neuron, let it run free and look at the same neuron. So what do we see for the same stimulus? Well, maybe we'll see something like this. So for 3 different trials with the same amount of time, you get very different spike trains. And the sort of conclusion is that single neurons are very noisy. We're going to talk about what noise means and all those properties in a second. But the fact that you get such variability here means that if you're storing information, actually either of these 2 ways, either by computing the average, which might help you get rid of the noise, or this way, where you're looking at the difference between spikes, like right here, the difference between spikes, it's fairly uniform here, but it's much bigger here, and here there's no other spike in this window to look at. So we get very different amounts of information. So when we're assuming that it's the same information that's being passed along because it's the same signals. So the fact that the single neurons are very noisy, and these 2 models both require fairly regular single neuron spikes, suggests that maybe looking at it in a single neuron, looking at information as being purely processed or encoded and decoded in single neurons is wrong. And so that we should look at something that would be more robust against the noise, which would be something looking at populations of neurons. Have you guys heard anything about like populations of neurons? It's like neural networks and populations of neurons, or neural populations are like sort of buzzwords, but in like popular sciences. No. Okay. Well, now you feel like it. So now we'll talk about relations. And so I'll kind of like here I'll just give you 2 models that again neither are perfect, but they're both sort of highlight some interesting aspects. So the first one is simply so you have like this neuron here, you have a whole bunch of other neurons here, and they're feeding into this neuron. And this neuron is trying to decide what to do. Well, it's instead of like looking at just one of these guys and saying, well, what's his mean rate or the amount of time in between the spikes, this guy here takes an average of what everybody's doing over a little bit. So this is the population average. What do I mean more specifically? So at a given time point, maybe this guy's firing, so this guy 1, this guy's not, this guy is, and this one's not. In which case, the average here is 2 over 5. So maybe, and this guy, say, has some sort of threshold. So if this guy fires if the average is, say, greater than 50%. So right now, it's so the whole reason I said that maybe we should start looking at populations of neurons just because there's a lot of noise in single neurons. How does that fix this? Or how does this fix that? So, say these guys fire, so this is 80% of them firing, so this guy will fire. Really, so, yeah.
So, just about the way that you're this new neuron, is this activation set of like an activation of some
Activation of, what do you mean by activation?
like an activation function, like
Oh, well.
damage.
Okay, good. Yeah, no. Well, it sort of is. So, I guess I didn't talk about it. There are a lot of different ways to do something like this. One way is you sort of do have an activation function. But right now, yeah, I'm just saying that the way this guy decides whether or not to fire is purely based on some sort of heart pressure. So it's saying if 50% of these guys fire, I'm firing at 50%, or 50% or more fire, I'm firing at under 50%. Which that's that, but you're good to other things. Yeah, okay, so say it's like this, in which case 80% fire. Well, like I said, these guys are kind of noisy, the individual neurons, so maybe instead of firing as it should, this one doesn't. There's, like I said, a lot of noise. Then you have a different number of neurons, and maybe this guy's connections firing, but because you still have 3 guys that are firing, then this guy still fires as it should. So effectively what I'm trying to say, and this is sort of intuitive, is just that if you have a lot, if you're looking at what a lot of people, what a lot of neurons are doing, even if the individual neurons are very noisy, the fact that you're sort of averaging over a whole bunch of other of these noisy guys means that you actually get a fairly reliable way of getting information. Does that make sense? So this is population averaging. So yeah, that was the first model I wanted to talk about. The other one is something called. A lot of these things are related, and I'm presenting them as separate. But you can imagine like that the population average model, instead of looking at whether these guys are actually firing, computes the time difference, and then decides based on that, or does like the rate of each one of these, and then figures out its own rate, or decides what its own rate should be. And then, with this next model, again, it's sort of connected, and so I don't want you to think these are all separate or all opposing, but I'm just presenting them as separate because I think it's easier to look at that. So the second model is a population. Did I spell it right? Spelling's not my strong. Okay, so synchrony. So you can imagine that one way to sort of more robustly, reliably code your information is to try and orchestrate with the whole population firing at sort of the same time. So for you to imagine that we have we have a whole lot of neurons, but if we imagine that we sort of split them up into these sort of regions, and these guys are connected to this one, so this is region 1, 2, and 3. So region 1 is connected to region 2 for the most part, and all the neurons, sorry, I should say all the neurons in region 1 are connected to region 2, and all the neurons in region 2 are connected to region 1. Then one way to and again, they're not connected to just one neuron. These guys are connected to a whole lot of these guys. These guys are connected to a whole lot of these guys. So one way to sort of send information more reliably and not let the noise get you as badly is to try and synchronize when each one of these guys fires. So if roughly all the neurons in region 1 fire at the same time, then even if there's some that don't fire because of noise, and even if you get lose some of that signal here because of noise, which we're going to talk about in a second when I get to noise, you'll still get a lot of these guys to activate because these guys all fire at the same time. So it's sort of like this, but now instead of these guys being sort of different, you're imagining that everybody's firing, and so of course this guy's going to fire based on the threshold. Like I was saying that earlier. And so then again, even if you lose some of these guys, if roughly everybody's firing, then this guy should fire, and that's a way of sending the information. Because in some ways, the synchrony is less a decoding method and more just a way of propagating information. But in some ways, I still think of it as encoding because you're still using these ways of encoding to push information. It makes no sense, but do people sort of understand encoding and decoding, or at least encoding? Any questions? Now we're going to talk about noise. So, does anyone have a definition for noise? Not like audible noise, but sort of signal noise. People know what I mean when I talk about noise.
Sounds.
No, so not about sound. I'm saying like signal processing noise. It's fine. It's fine. Any other clues? Yep.
Like extra unneeded or unhelpful data that's has a possibility of application.
Sure, that's pretty close. So I think the way I think about it is sort of disruptions to your signal that cause your signal to change in some way. And they're sort of typically random fluctuations. And like the reason, one way to think about it is if you have like a sound speaker or something, speaker you're playing music, sometimes you hear that like crackly sound. That's like noise, signal processing noise affecting your music, and then you get an actual noise. Yeah.
I think I know what you're talking about, like kind of like static.
Yeah, it's like static to your signal.
Like I know about like white noise where it makes that noise and it's like a bunch of white and black pixels just bouncing around your screen.
Yeah, no, that's right. So does anyone know why white noise is called white noise? Okay. It's because white noise is made up of every possible frequency of every possible. It's made up of lots and lots of frequencies, and sort of like white light. White light's made up of every sort of visible frequency of light. White noise is made up of every sort of audible frequency, and so it has a lot of interesting properties. And we're actually going to talk about one when we talk about how noise is actually something helpful. So most of the time, noise is not helpful, and the way of we've been talking about like signals in terms of audible, but you can also imagine like if you have a line, the noise might like make your line disrupt exactly the straightness of it and cause it to be more rigid. But it's maybe not just disrupting the signal, it could also just be, I guess, additional signal, which is so stuff that you're not actually trying to send, but gets sort of added into what you're sending. And so something like this, or like what you were talking about with the white noise, sometimes when you play music really loud or you have like bad speakers, you get that sort of static. And that's because you're doing a couple things, but like one thing you can sort of think about is you get an additional signal versus disrupting. So one thing that's one reason I like biology and neuroscience a lot, even though I'm not one more of a math and physics major is because of these problems with noise. And noise, biological systems are extremely noisy. And that the fact that we have reliable, so that biological systems are still reliable is pretty crazy. So, like I was saying, with here, with these single neurons, they're unreliable in the fact that they're susceptible, very susceptible to noise. So, and I'll talk about exactly where that noise comes in, but here, because they're susceptible to noise, they're unreliable as information carriers, and yet the fact that we can routinely process information the same way, even though these individual neurons are unreliable, is pretty cool, I think. So, what exactly, where exactly does the noise come from in neural systems? Does anyone have an idea? Okay, so sort of what I was saying. I don't like independent about what the is. Good. So, there's noise in stimulus recording. So, for instance, this is less noise in the neural system, but noise in actually trying to connect what your stimulus is to how you're reacting or how the information is being encoded. This comes up. So, in your eyes, for instance, photoreceptors that are very sensitive, and then but sometimes they get triggered when the light hasn't hit them, or they sometimes pulse as though a different frequency hit them. There's a lot of noisiness in how photoreceptors see what we see. So what our brain is, the very stimulus that our brain is getting is often a little corrupted from what we're actually seeing. What actually is actually because of the mechanism to record. So that's one area. Another area of noise is in the neurotransmitters. So sometimes the neurotransmitters, because I don't know if you remember, I just erased it, but we have these two neurons, and we've got these little receptors, and they're neurotransmitters, and they come down and get connected to these receptors. This is the way that these guys travel is random in nature, so that when they come out here, they're not going straight down. They're sort of going all over the place. Even if there's a general flow downwards towards these receptors, the number of neurotransmitters that actually hits these receptors is variable, which means like it doesn't happen the same amount every time. So it's been sort of recognized that sometimes neurons fire when they shouldn't have because there are lots of neurotransmitters here before they sort of still hang out. And they get bound to these receptors. And sometimes neurons don't fire when they should because not enough of these transmitters actually hit the receptors. And that's where you also get noise in when exactly the neuron fires, because sometimes it takes a little bit longer to fire and sometimes it doesn't. So here, these guys fire at roughly the same time, but there's still a little discrepancy in when they do. And that's at least good. This is just hypothetical, but it can possibly because of this sort of process. The neuro. And then there's also just sometimes because, so actually no, so I didn't talk about this, but there's another sort of way in which a neuron might fire, and that's where has some sort of threshold, and when its neighbors fire, its action potential gets raised higher and higher up, and once it crosses this threshold, then it eventually fires. And so maybe its neighbors, because of neurotransmitter noise, Or other things, maybe its neighbors don't fire as strongly, and so then that means that this guy doesn't actually reach its threshold, so maybe it comes up here and falls back down. And so that neuron never fired. So, I guess that's sort of related to this, but the fact that you're connected to a lot of neurons means that if one neuron doesn't do what it's supposed to do, then maybe another neuron doesn't either, and that sort of propagates around. So, yes, radiation of errors. Yeah, and so these are three potential sources, or not just potential, but they happen all the time, sources of noise. And these all sort of corrupt the signal, make it different from what it should be. So now I just want to get to this idea of stochastic resonance, and then we'll do a little bit of neural networks. So stochastic resonance, what is that? Okay, so this is the sort of, at least initially counterintuitive notion that by adding noise, you can increase your signal to noise. Which, when I just learned about this recently, actually, so that's something that's I don't think often taught, and it does seem very counterintuitive. How can adding more noise boost your signal to noise ratio? I guess I should say, so people know what I mean by signal to noise ratio. Sort of. Does anyone want to try? Yes.
Guess the actual signal versus the
Yeah, that's a good explanation. So like, well, I guess I erased it, but when I drew this line and then I drew this sort of line that has some noise to it, the signal to noise ratio measures how much this signal actually gets corrupted. And another way of thinking about this is like with your sound speaker, if you just hear a little bit of crackling, which more like practically all speakers have, all of them have some sort of, there's a little bit of noise, most of the time it's not noticeable if you have like a good speaker, but if you have a bad speaker and it's very present, noticeable, then you have a very high signal to noise ratio, or a very low signal to noise ratio because there's a lot more noise. That's sort of distracting from this. And so how is it that by adding noise you can increase your signal to noise ratio so you get a better, cleaner signal? And so to sort of illustrate, I'll draw an example. So say I drew this picture and I got lazy. And so there should be an actual picture. Can anyone guess what I was sort of going for? Probably not, right? Because it's not just one line. But now say I place down some dots, right? And keep in mind I had an idea in mind. And so if I place down dots, maybe you'll see an actual picture, right? Or of something that I might have drawn. Put it down here, and down here. These dots should be sort of random. How does it look like anything? Yeah, literally. Maybe this sort of looks like a smiley face, right? You have the eyes, you have the mouth. So even though you have all these other dots, you actually see, not but you can sort of see this smile, right? And so but before there was no noise. All I drew was something that I specifically wanted to draw. But then by adding noise, you can actually, especially since I intended to draw a smiley face, but I didn't, and now you can sort of pick out the smiley face. I've increased my signal. It's sort of an example. I don't know how you can.
So is it just by chance?
No, well, so I cheated and put 2 dots here. Because stochastic means random, and so these dots really should have been random. And so if some sort of threshold is to say I had really small dots, then I have to put a lot down before I got the 2 that are like near here. And in that case, there'd be probably dots everywhere. You wouldn't be able to sort of notice this amount of things. But because I got 2 big dots, and because I cheated, or even if I didn't cheat, I could still get lucky, like so chance and actually boost it. And so what stochastic resonance really is say you have a very weak signal, so a signal that's not something that you can maybe detect by adding white noise, which you brought up, where you have sort of a frequency, you have all frequencies, you can raise the frequency that you're actually trying to send, and you can make it stronger. Does that make sense? It's counterintuitive until then you think about it some and then it's being a little bit more intuitive. But listen now, this was meant to illustrate it a little bit without I think it's I think it's a little different idea, but yeah, I'd say that I mean maybe it helps resonate like certain thoughts you have, but this is more just like sorry. So I guess I should. This might seem a little unconnected to what we've been talking about with neural systems, but the reason I bring it up is because despite having some downsides to having one thing people sort of think is that the brain has a lot of noise, and maybe even more noise than you might expect, because more noise than you might need if you designed it a little bit more carefully. Which I'm not saying that the brain was designed, evolution shaped it, but you could still imagine maybe half that evolution you could take to shape it in a little bit of a way that there would be less noise. But even so. People are sort of coming to this idea that, well, maybe the brain has a lot of noise on purpose, and part of that is because of stochastic resonance, boosting the information, even though you have these same things. So I thought it was just a cool. Okay, and now, since we have 10 minutes of the little neural network stuff, does anybody, but again, like I was saying, that's sort of a buzzword, but does anyone sort of have a idea of what a neural network actually is? Yeah.
Mathematical model to represent decisions.
Okay. Yeah. So I think of it as being a model that attempts to replicate some sort of aspect of something that's done by it. So like decision making, or in this case we'll talk about memory recall. So how is it that if you hear like a little melody, you can recall a whole song, or you see like a part of someone's name or the full name, how is it that you're able to recall memories based on limited symptoms? Yeah.
So it's like it's how the system
Okay, so first I should say I don't know so much about Alzheimer's. I was under the impression that one issue with Alzheimer's, I got rid of the drug, but you have dendrites. Maybe. I thought, and I totally could be wrong, but so there's something called the myelin sheath right here, and this insulates it just like with wires, like an actual wire in a house. You have like some insulators to keep the electrical current contained. But as you get older, everybody's myelin sheaths get deteriorate, but some people more than others. And so then you can actually sort of like these bare wires, and then these interfere with each other, and so you get a lot of issues. That's what I know about Alzheimer's. So this memory recall, it has applications to Alzheimer's, but a little bit more limited. we're going to talk about the hot field network. It was published in 1982. So fairly, I don't know, I guess it's fairly recent as science things go. It was developed by this guy named J.J. Hopfield, a physicist who's turned into sort of more of a neuroscientist and biologist. And if you had ever studied physics, you might come across an Ising model, which talks about how electron spins interact with each other, and effectively he used that sort of model for his. So, I'm not gonna. I think I'm gonna, instead of writing out the actual math, I'm just gonna sort of draw the concept of this hot field. Also, we're doing it. So, imagine this is one thing. If you take higher level math courses, you tend to abstract more. And so, we're going to abstract all the sort of possible memories you can have. Okay, so first I guess I should say, set up for this network that we're going to be considering. Say we have n neurons, and what we're doing is we're saying that each one can be either 1 or 0, and we're storing a particular memory. And by memory, I mean a particular state of these neurons. So we have like a list of neuron 1's activity, neurons 2 activity, all the way down to neuron n, and these values appear to either be 0 or 1. And we're storing them. So this sort of circle I've drawn, this represents memory space. So these are all the possible memories we can have. If you want to get technical, it would be an n-dimensional space, so it could be much higher than 3 dimensions, but we don't care because it's not a physical thing, we're just considering. So now say I store a memory. The hot field network, the way it works, when you store a memory, you sort of loosely you distort this memory space. So say I store this memory. Have you guys ever heard of the sort of popular science way of thinking about general relativity? You have like a plastic sheet, you put something heavy down, and then that creates like bends that plastic sheet, and then if you put something that's much smaller, it'll sort of fall into that orbit, or fall into the space that's the thing that's the space is the heavier thing that's deformed the sheet. This is sort of similar in the sense that this memory, the way that hot field network works is when you store a memory, anybody that's close by gets driven in to keep. So this is what's called an entrapment. So stored memory is an entrapment. And I guess I should say, so the way you store it, because I'm not going to go into the math as much, I'll just tell you how you store this memory. The way you store the memory is by adjusting the connections, the strength of connection between neurons. And you assign a value of either 1 or -1. And 1 is if this memory is sort of So, say we take a specific memory, so this is memory X. X, 1, 0, 1, whatever. It's some list of these activities, right? Now the way the hot field network stores this memory is through the connection, and so neuron 1 and neuron 2 are connected, get a -1 value for connection because they're doing opposite things. Whereas 5 and 6, neurons 5 and 6, they get a positive 1 of connection because they're doing the same thing. So formally, the connectivity is so for neuron I and J, they're connected with strength 2 minus VI is just the value that's in here. I guess I should put all this next to it. So I and j are just some integers that fall in that are less than the number of neurons, and then the connectivity is minus. Does that make sense? So you see that you can either have, yes, you can either have positive connection, 1 or negative connection, negative 1, because if these guys are doing the same thing, so they're both 1, then this is 1, and this is 1, so you have 1 times 1 is 1, and if these are 0, then you have negative 1 and negative 1, and that's 1. But if these guys are doing opposite things, then this will be 1 and this will be negative 1. And so effectively, by storing the connection, by storing the memory in the connectivity, you make the memory that you've stored be an attractor. So anything in this range falls in. And so then you can keep storing memories. Right? And the interesting thing, and I guess I'll sort of end with this, the interesting thing is, and I guess it sort of goes back to your Alzheimer's question, sort of, is say I store a lot of these memories. Okay, so a lot of memories. Right? And so this memory space is full of attractors. Now say I get some partial information, which that's what the little thing here moving towards the attractor represents, that you end up with in memory. Say I have like some partial information, like someone's first name, I'm trying to remember their last name. Because this is close to 2 attractors, which one it falls into depends exactly on where it is. So even a little bit of a bump from here to here or whatever, then you fall into this one instead of this one. And I guess I should say, so I was imagining this as being like someone's name or something, and you remembering them. This is just a potential model, and it's not actually accurate. It's not how our brains actually remember people's names, but in terms of like machine learning and stuff, you can use this model to get memory-like properties. But even though they're different from how we remember things, it's still a valid way of making machines sort of memory recall, and it's still a nice model that has a nice property. Did you have a question?
Yeah.
Yeah.
My question was
Okay, sure. Well, anyway.
okay. So when I've looked at like neural networks in the past, they're almost always in the form of like a grid of neurons and layers. Is this just like a different visualization of like long-term memory?
Okay, so there are definitely a lot of different neural networks, and this is just one I chose because I thought it had a nice sort of visual way of thinking about it, and had a nice sort of connection to something neurological. So you can have layers, and that sort of that deals with it's just, those models are much more common, and those I think often address different things. And so I honestly don't know which ones we looked at, and I don't know. I'm definitely not an expert in any of those. But at least regarding this one, it's just imagine it's single. Thank you so much. Nice time. And do the rest of your